Hello. Measuring a network is the best way to get first-hand information about how it's performing. With 5G and the cloud demanding more from networks, network O&M is only getting harder, making visibility on performance ever more key. So customers now want and expect better performance from network measurement technologies. What does this mean? We're lucky to have Jutin Ran join us today. He's an expert from Huawei's Data Communications Standard and Patent Department, and he's going to help us explore the evolution of network measurement technologies. Hello, Mr. Zhou.
Hello, it's good to be here.
Mr. Zhou, could you outline for us the basic types of network measurement technologies?
We usually classify network measurement into three categories: proactive, passive, and hybrid. Proactive measurement requires test packets to be sent on a network. Network behavior is analyzed according to the characteristic changes to the packets. Typical methods include ping, traceroute, and TWAMP. Passive measurement is different. It doesn't inject test packets or modify service packets at all. Instead, it measures network status, traffic characteristics, and performance parameters by obtaining the headers of the packets passing through certain measurement points. S-flow and IP-fix are typical methods, and hybrid measurement is somewhere in between. It marks data packets and performs coordinated measurement of a network. Methods include IPFPM and IFIT.
Can you briefly describe the advantages, disadvantages, and uses of these different measurement technologies?
Proactive measurement methods are flexible, but they eat up bandwidth and take up some of a network's processing overhead. Plus, the test packets that are sent can actually affect the measurement result. For example, TWAMP, which is a widely used proactive measurement technology, constructs test flows based on 5-tuple information, using the response packets that it receives to measure the performance and status of IP links. Although TWAMP has low measurement precision and does not support hop-by-hop measurement, it's highly available and deployable. NEs don't need to generate or maintain statistics. Plus, the performance management system can obtain network-wide performance statistics by simply connecting to the node that initiates the test.
And can you contrast this method with passive and hybrid measurement?
Passive measurement does not affect network performance and is relatively accurate. However, it can only monitor the local status of network nodes. Hybrid measurement combines the advantages of proactive and passive measurement. It can obtain accurate measurement data using only a small amount of marking in data packets. The in-band flow measurement methods that have emerged in recent years belong to hybrid measurement.
Can you explain what increasingly popular in-band flow measurement actually is?
In-band flow measurement is a relatively new hybrid measurement method. It collects network status information by inserting metadata into data packets on transit nodes along a path and in sequence. Compared with traditional network measurement solutions, it implements finer-grained packet-level measurement.
Can you help us understand the concept a little better?
Let's compare in-band flow measurement to monitoring the condition of a physical road. Think of it like this: a network is a road, and the services it carries are vehicles running along it. Traditional proactive measurement indirectly determines network quality by sending test packets. This is like placing a limited number of cameras at fixed positions along the road. Inevitably, there are blind spots between the cameras. In contrast, in-band flow measurement is like installing a dash cam in every single vehicle using the road. All of this dash cam information is summarized, and the delay and packet loss information of any specified service flow can be measured instantly.
So, in-band flow measurement overcomes the shortcomings of more traditional methods?
Yes, using traditional measurement, faults are usually located once a fault alarm is generated or a complaint is received. In other words, it's only reactive. And as networks get bigger, finding faults is only going to become more and more difficult. It can take days, even weeks, to locate a fault. That's going to be a big problem for the kind of innovative services that will place higher requirements on network O&M.
What do you mean by that, more precisely?
For example, the development of 5G has given rise to new services, from HD video and VR to the Internet of Vehicles, to support unified management and reduce maintenance costs. The cloudification of network devices and services is well underway. Facing a new window of opportunity, we need to use innovative technologies to address the diverse challenges of these new services.
Okay, so how does in-band flow measurement help here?
In-band flow measurement technology has two basic modes, passport and postcard, depending on how collected data is processed. Passport mode is like a world traveler whose passport is stamped every time they enter and leave a country. Transit nodes collect data hop by hop and record it in packets. The egress in the measurement domain sends all collected data to the collector and restores the data packets. Postcard mode is like a tourist sending a postcard home from each tourist site visited. When each node in the measurement domain receives a data packet, it does not record it. Instead, it generates a packet and sends it to the collector.
What are the advantages and disadvantages of these two modes?
In passport mode, packets are only sent by the egress in a measurement domain. This means a smaller reporting overhead. And the collector doesn't need to associate packets with node data, unlike in postcard mode, where the collector must do this. But in passport mode, the packet header expands as the number of hops does, making it difficult to identify the precise location of any packet loss. In contrast, in postcard mode, the packet header is fixed and short, plus hardware-based implementation is simple, so the location of any packet loss is easy to find.
What are typical in-band flow measurement methods?
IOAM, IPFPM, and IFIT to name a few.
Can you tell us more about them?
IOAM samples service traffic in real time and at high speed, adds IOAM information to sampled packets, and sends the collected data to the analyzer for analysis on the egress. So network running status can be detected and monitored in real time. This technology uses the passport mode and features rich functions and good scalability. But it also has disadvantages. The packet header is expanded, hardware-based implementation is difficult, transmission efficiency is low, and hop-by-hop packet loss measurement is not supported.
And what about IPFPM?
IPFPM is a technology that uses flow identification and coloring to monitor network packet loss and delay, implementing end-to-end performance measurement. It supports various different kinds of application, collects a small amount of data, and has little impact on forwarding plane performance. However, it uses a sampling mode for delay measurement and cannot completely measure packets. Even worse, it has weak scalability, so hop-by-hop deployment is difficult.
Which mode does IFIT belong to, and why is it proving so popular?
In situ flow information telemetry, IFIT for short, uses the postcard mode that we mentioned earlier. It carries the telemetry instruction header in user packets and reports data hop by hop on transit nodes. Compared with IOAM, IFIT has a short and fixed header, which has little impact on the forwarding plane's efficiency. And IFIT supports hop-by-hop packet loss measurement. Compared with IPFPM, IFIT really simplifies deployment, improving its efficiency by some 80% and improves scalability, meeting long-term network evolution needs.
Thank you, Mr. Chu, for your time, and thank you for watching. I hope you'll join us again to look more closely into IFIT. Goodbye.